All right, lesson 2, rates of change. And so our skills and learning objectives are we're going to find the average rate of change of a function over an interval. We're going to find the rate of change at a point using small intervals containing the point. We're going to describe the relationship between the rate of change and the behavior of the function. So in lesson 2a, rates of change, it says we have seen that the slope of a line can be interpreted as its rate of change. The rate of change function is defined as the rate at which the output quantity changes with respect to the input quantity. If the graph of a function is not a straight line, we use the terminology of an average rate of change between any 2 points on the graph. And so if our function is not linear, we can still find the slope of the line that connects 2 points on the nonlinear function. And we just call that the average rate of change. So here it says the average rate of change between two input values is the total change of the function values, the output, divided by the change in the input values, given the value of a function at different points x1, y1, and x2, y2. So the average rate of change on f in the interval from x1 to x2, where f of x1 is equal to y1 and f of x2 is equal to y2, is just going to be the same as the slope. It's going to be y2 minus y1 over x2 minus x1. So example 1 says to find the average rate of change of f of x equals x cubed minus 4x over the interval, and it should say from 1 to 3. All right, so the difference is it gave me my x1 and my y1, but it did not give me, it gave me my x1 and my x2. It did not give me my y1 and my y2. So we know our x1 is going to be 1, and we also know our x2 is going to be 3 because that's the interval, those are the x values. But I need to go find my y1, and so in order to find y1, we can just plug that into our equation. We can plug x1 in, so we're looking for f of 1, which my equation was x cubed minus 4x. So I'll plug in that 1, and I'm going to solve it. And so I know that y1 is negative 3. And then I'm going to scoot my x2 down a little bit here so I can write underneath it. And so we said x2 was going to be 3. So I'm going to go find y2 by plugging it into the equation. So I'm looking for f of 3. So I'm going to plug 3 in. And so I found that my y2 is going to be 15. So we know x1, y1, we know x2, y2, so now we can just go find our average rate of change. So our average rate of change is equal to, remember the formula, y2 minus y1 over x2 minus x1, just our slope formula. So I'll make my skeleton here. My y2 was 15, my y1 is negative 3, my x2 is 3, and my x1 is 1. So I'm going to do this. I get what, 18 over 2, which is 9. And so we know our average rate of change is 9. All right, example 2. So the table below is data from the University of Michigan Center for Sustainable Systems that shows a U.S. annual municipal solid waste generation. MSW is commonly called trash or garbage, which generally refers to common household, office, and retail waste, but excludes industrial, hazardous, and construction waste. A says to find the average rate of change in trash between 1985 and 1990. All right, so we know then that x1 is going to be, let's say, 1985. And we're going to let x2, write it down here, now write it beside it. And x2 is going to be 1990. All right, so I can see the y values by looking at my table. In 1985, its y value is 166.3. So that's going to be my y1. In 1990, its y value is going to be 208.3, so that's going to be my y2. And then we're we're just looking for that average rate of change. So we know it's going to be the 208.3 minus 166.3 over 1990 minus 1985. All right, so I'm just going to plug that in my calculator, and it's going to tell me 8.4, and I know that this is labeled in million tons. It's a million tons per year. All right, B, so did the rate of trash ever decline in this 58-year period? When, and what was the average rate during this period? So just look at the numbers there, and did it ever decline? See it increase, 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 increase. All right, oops, turn my pen right here, it went down. All right, and then it's increasing again. So yes. The rate decreased between 2005 and 2010. Whoops. Okay. When we stated that, what was the average rate during this period? All right, so in 2005, it was 253.7. And in 2010, it was 251.1. Okay, X1, Y1, X2, Y2. So my average rate of change. All right, and so we can see it went down. It decreased by 0.52 million tons. Per year. So I don't know if I'd leave it as negative 0.52 million tons. I would probably put that it decreased by 0.52 million tons per year. So I'm going to come back over here to my sentence. So yes, the rate decreased between 2005 and 2010 by 0.52 million tons per year. All right, example 3. It says, after surgery, you are given a pain reliever. The level of the medication will decrease slowly over time. Let CFT represent the medicine's concentration in your body. Write an expression for the rated change of the medicine's concentration level over a period from T equals 15 minutes to T equals 90 minutes. All right, so we don't actually know an equation to be able to get a Y value here for it. So we know it's going to be 15 comma something, and we also know that it would be 90 comma something. Now, just like any time we're going to plug in like X, we can see it as F of X. So I'm going to do C for concentration of that 15, and then here my Y value would be the concentration at the at the 90 minutes. All right, so then my average rate of change will equal the Y2 minus the Y1 over x2 minus x1. And now we can't simplify the top, so we're just going to leave it as it is because it just wants the expression. So we're just wanting like kind of an equation, something to help us with it, over, but I can simplify the bottom. And so that is what we will get as our expression. All right, then example 4, distance versus time graphs. So it says, let's explore the distance a car travels over a 2-hour period shown at the right. What is the average rate the car travels? And so we can look at it from the beginning to the end. So we can look at it when time is 0. And when time is, what's the last one on there, 120? All right, so when time is 0, the distance is 0. And when time is 120, the distance is that 100? Yeah. Okay, there's my x1, y1, x2, y2. So for my average rate of change, let me y1 or y2 minus y1 over x2 minus x1. See, our y's was a distance, so that's in miles, and the x's were the time, which is in minutes. So they went 5 miles every 6 minutes. And so if we want to change that to like miles per hour, so I'm going to come down here. So we have 5 miles every 6 minutes. And so I'm going to do a little conversion here. So I know that 60 minutes is 1 hour. And so my minutes will change. So that gives me, is that 50? And it's miles per hour. All right, how fast is the car going from when t equals 30 minutes to t equals 60 minutes? Be sure to change the minutes into hours. So when t is 30 minutes, the distance is about 20. And when time is 60 minutes, the distance is about 40. All right, so 40 minus 20 over 60 minus 30. So it's at 20 over 30. So 2 miles every 3 minutes. I want to change that to miles per hour. So I know 60 minutes is in 1 hour. So that gives me 40 miles per hour. All right, C says, when is the car traveling the fastest and how fast is it? Well, we're looking at for where it's the steepest, which is going to be between, it looks like 70 minutes and 90 minutes. And it says how fast. So it's 70 minutes. The distance is 50. And at 90 minutes, oops. The distance is 80. All right, so my average rate of change is 30 over 20. So 3 miles every 2 minutes. And I'm going to change that to miles per hour. It should give me 90 miles per hour. All right, D says, what is the slope of the graph between t equals 90 and t equals 120 minutes? And what does the slope represent in relation to the context of this problem? All right, so we got t equals 90 and t equals 120 minutes. So let's see, at 90, we know that our distance is 80. And 120, we know our distance is 100. And so we can find that average rate of change. So it's 2 miles every 3 minutes. And so I'm going to convert that. So 60 minutes is 1 hour. So that's 40 miles per hour. So it says now what does the slope represent in relation to the context of the problem? That means the average rate of travel, the slope is the average rate of travel on the interval from 90 to 120 minutes. All right, and E said, what is the speed of the car at 45 minutes? Well, 45 is, let's see, some good points that they gave us. Maybe like 40 and 60 to help us there, get us close. It's kind of in a nice interval that's got nice, pretty points. So when time is 40, we can see our distance is 30. And when the time is 60, we know our distance is 40. And so the average rate of change in between those two so it's 1 mile every 2 minutes. So it comes out to be about 30 miles per hour. So we can assume that the speed of the car at 45 minutes, the average is going to be around the 30 miles per hour.